Welcome back to the deep dive. Usually when we talk about language, we get almost poetic about it. We talk about it as this, river of culture or the tool for storytelling.
The art of being human. It's how we express the inexpressible.
Right, exactly.
Uh,
But today, we are throwing all that poetry out the window. We're ignoring the art.
We're popping the hood.
We are popping the hood and looking at the biological machine inside your head that makes it all possible. We've got a stack of research here, specifically focused on the computational component of the language faculty. This is from Chapter 4 of Chomsky's Minimalist program.
Which is, yeah, that's a heavy hitter. This is not light reading. It's basically the technical blueprints for the computer inside your brain.
And that's our mission today. We want to understand how the brain takes just a random grab bag of words and somehow spins them into a structured sentence. And we're not talking about why we say things. We're talking pure mechanics.
The nuts and bolts. If your brain is a factory, we're looking at the conveyor belt. We are looking at the system. In the text, they call it CHL, the computation of human language. And the first thing you have to get your head around is that this system is, at its core, just an input-output machine. It's an algorithm.
Okay, so every algorithm needs an input. What are we feeding this thing?
You feed it a collection of choices, lexical choices. You basically reach into your mental dictionary and pull out the raw ingredients for a specific thought.
And the output is?
The output is a pair. And this is really crucial. The machine has to produce two things at the same time, sound and meaning.
Two totally separate signals.
Yep. In the technical notation from the source, sound is pi, the Greek letter, and meaning is lambda. So the machine runs, and if it succeeds, it spits out a sound structure for your mouth and ears and a meaning structure for your conceptual system.
It sounds simple when you put it like that, but the text makes a really big deal about a compatibility requirement.
Right. You can't just pair any old sound with any meaning. If you start with the ingredients for the cat sat on the mat, the machine can't output the sound for the dog ate the bone.
The sound and the meaning have to come from the exact same starting set of words.
They have to be derived from the same source. Exactly.
Okay, let's talk about that starting set. The text calls it the numeration. To me, this felt like the most concrete part of the theory. It's basically a shopping list, right?
That is the best analogy for it. The numeration, which they call $, is your basket. Before you build a sentence, you go to the store of your memory and you pick out exactly what you need.
But there's a technical catch.
There is. You don't just throw the word cat in the basket. You throw in a pair. The item itself, cat, and an index.
An index. That's just a fancy word for a number, isn't it?
It's a counter. It tells the system how many times you plan to use that item.
So if I want to say, the cat saw the dog, I need the word the twice. One for the cat, one for the dog.
Correct. So in your numeration basket, the entry for the would have an index of 2. Cat has an index of 1. Saw has an index of 1, and so on.
Wait, hold on. Does that mean my brain has to, does it have to pre-plan the entire sentence before I even start speaking? I have to know I need two thers before I open my mouth.
In this model.
Yes.
Yes, that's the implication. It's a pre-selected array. You don't just grab words on the fly. The system loads the buffer, and then its job is to process that buffer until it's empty.
And the machine uses these numbers to play a game.
A countdown game. This is the core mechanic. Every time the system uses a word, it subtracts 1 from its index. So you use the 2 becomes a 1, use it again, the 1 becomes a 0.
And the main rule is the basket has to be totally empty at the end.
Completely empty. A computation is not a valid derivation. It's not a real sentence unless every single one of those indices hits 0.
Use it or lose it.
More like use it all or the whole thing fails.
Yeah.
If you finish the sentence and you still have a the left in the basket with an index of 1, the system crashes. It's not just a bad sentence, it's a failed computation. It didn't converge.
That's weirdly strict. It's like baking a cake where if you have one egg left over, the whole oven just explodes.
Or it just refuses to turn on. But yes,
yeah.
The derivation crashes. The system is designed for efficiency. It pulls from this pre-selected list, and it has to exhaust it.
Okay, so we have the basket. The numeration is full. Now we actually have to do something with it. The text details 2 operations that it calls costless, select, and merge.
Right. These are the freebies, the free tools.
Why free? Is there some kind of a budget?
In minimalism, yes.
Yep.
Absolutely. We talk about economy. The brain is fundamentally lazy. It wants to do the least amount of work possible. Some operations are expensive. They cost something. But select and merge are considered costless.
Okay, let's break them down. Select seems pretty obvious from what we just said.
Select is just the act of reaching into the basket. You pick an item. You lower its counter by 1. You're taking a brick out of the pile. You can't build anything without picking up a brick. So the theory says this operation is free. It's just a given.
And merge.
Merge is the engine. It's the combiner. You have two objects in your workspace. Say the word Z and the word cat. Merge takes these two separate things and it glues them together into a new single object, the cat.
And this is also free. Why?
It has to be. I mean, if you didn't merge things, you just have a random list of words. You wouldn't have any structure. You wouldn't have language. The text makes a point here. It's like asking why a calculator adds 2 and 2.
It's just what the machine does.
It's what it is. If select doesn't happen, the numeration isn't emptied. If merge doesn't happen, nothing gets connected. Since they are the absolute bare necessities, they don't count against the brain's economy. They're free passes.
Okay, so we're selecting from the basket, we're merging, we're building up the structure piece by piece, but then the text introduces this huge plot twist, the fork in the road.
Spell out.
It sounds like a command from a fantasy novel, but in this context, it's a specific moment in the process, right?
It's the critical pivot point. Up until this moment, the computation is what we call overt. We're moving these word objects around. But at some point, the system has to deliver the goods. It has to send the sound to the mouth and the meaning to the mind.
The pi and the lambda we mentioned at the start.
Right. And spell out is the moment the system splits the signal. It takes the structure you've built and it literally strips away all the parts that are only relevant for sound.
It strips them away.
Yes. It sends the phonological information, the vowel sounds, the consonants, all that, down one track to what's called the phonetic form, or PF. And everything else continues on down the other track to the logical form, or LF.
Why separate them? Why not just send the whole package to both places? Why can't my meaning brain, so to speak, handle sound information?
Because the meaning department of your brain, the conceptual system, is basically allergic to sound. Think about it. Your ability to understand the concept of justice, or cat, has absolutely nothing to do with whether the vowel is long or short, or if it starts with a K sound. To the conceptual system, that's just noise. The text is clear. If phonological features reach the logical form, the derivation crashes.
So spell out is a filter.
It's a purification system. It says, okay, all you sound features, you go to the ear. All you meaning features, you go to the brain.
I'm picturing like peeling a banana. You peel it, you throw the skin, that's the sound one way, and the fruit, the meaning, goes into your stomach.
And you can't digest the peel.
Right. If the peel gets into the stomach, the logical form, you get a stomach ache. The system crashes.
That's a principle called full interpretation. Every single element that arrives at an interface has to be usable. And the meaning system can't use sound, so the sound has to be stripped away before it gets there.
This all leads to a really interesting idea in the source. The inclusiveness condition, this sort of ideal of perfect language.
This is Chomsky. The ideal perfect system would be one where nothing new is added during the whole process. You just take the features that were in the dictionary, you rearrange them, and that's it. You don't add new tags or markers.
No preservatives, no artificial colors, just the raw ingredients.
Precisely. And the text argues that the path to meaning, to the logical form, is actually pretty close to this perfect ideal. It's clean.
But the path to sound?
The path to sound is messy. And that brings us to the most controversial part of this whole engine. Movement.
Okay, yeah. This is the part I really struggled with at first. If merge is free and select is free, why is moving words around considered expensive? And why do we even do it? Why not just speak the words in the order we merged them?
That is the big question. In a perfect world, we wouldn't move anything. So the theory has to assume that movement is a last resort.
We only do it if there's a gun to our head?
Metaphorically, yes. We only move a word if the derivation is going to crash otherwise.
Can you give me a concrete example? Because movement feels a little abstract.
Sure. Think about a simple question. I can say, John bought a book. Simple. John is the subject. Book is the object. But if I want to ask what he bought, I have to say, what did John buy?
Okay, so the word what is at the very beginning of the sentence.
Right. But logically, what is the object of the verb buy?
Yeah.
In terms of meaning, it belongs right next to buy, just like book did. But in English, for some reason, we are forced to move it all the way to the front.
So we took the word what and physically dragged it across the sentence structure.
That's it. That is overt movement.
Yeah.
And the minimalist program's obsessed with the question, why?
Yeah.
Why spend the energy to do that?
And the answer is features.
Features. Specifically something called strong features.
Okay, let's unpack features. Everything in this theory seems to run on features.
Think of a word not as one single thing, but as a bundle of properties. Take the word airplane. It has phonological features,
Hmm.
what it sounds like. Those get stripped away at spell out. It has semantic features. It's an artifact. It flies. Those go to the meaning side. But it also has what we call formal features.
Formal features like
Yeah,
it's a noun.
exactly. It's nominal, or maybe it's plural. These are the instructions for the machine. And some of these formal features are dangerous. The text calls them strong features.
Dangerous how?
The derivation cannot tolerate them. A strong feature is like a hot potato or a virus. It enters the structure, and the system basically screams, check this off and delete it immediately.
And immediately has to mean before spell out.
Yes, that's the crucial connection. Remember, at spell out, the sound gets stripped away. So if you have a feature that requires you to change the word order like moving what to the start of the sentence to mark it as a question, you have to do it before the sound is sent off to the mouth.
Because if you wait until after spell out.
The sound is gone. You can't move the sound of a word if you've already mailed it to the speakers.
So a strong feature forces overt movement. It's a command that says, move this word N now W so we can check this feature off before we split the signal.
That's it exactly. It triggers a rule. The text also mentions cyclicity here. You can't skip it. As soon as a strong feature enters the derivation, you have to deal with it right then and there. You can't merge 5 other things and then say, oh, let me go back and fix that hot potato.
And if you don't?
Crash. The feature isn't checked. It survives all the way to the interface, and since it's uninterpretable there, the whole system just fails.
So to go back to the what did John buy example, there's a strong feature in that question position at the start of the sentence that works like a magnet.
That's a perfect way to put it. It's a magnet that is so powerful it rips the word what from the end of the structure and pulls it all the way to the top. And it must do that before spell out takes the sound away. That's why movement happens. It's a rescue operation to satisfy a strong feature.
It's fascinating that our brain is doing this high-stakes juggling act every time we make a simple sentence. Move this, delete that, strip this sound. And it all happens in milliseconds.
It really does make you appreciate the complexity. And we haven't even talked about where these features come from in the first place. We've been talking about the numeration, the basket, but where's the store?
The lexicon.
The lexicon.
Wow.
The dictionary in your head.
Now, I always assumed the lexicon was just a big list of every single word I know, but the text defines it in a very specific way. It calls it a list of exceptions.
This is one of the most, I think, insightful parts of the minimalist program. We tend to think our brain just stores everything, but storage is metabolically expensive.
Right.
An efficient system only stores what it absolutely cannot predict.
Idiosyncrasies.
Exactly. So take the word book. Does your brain need to store that book is a noun? Yes, because you can't guess that from the sound book.
Yeah.
Does it need to store the sound itself? Yes, that's arbitrary. So those things are in the lexicon.
Okay. But what isn't in there?
Plurality. Case. The text argues that the entry for book does not contain the word books.
Wait, hold on. So you're telling me the word books with an S is not actually in my mental dictionary?
Not as a separate fixed entry, no. Think about it. If you stored book and books and books and books, you're just wasting space. You can predict the plural. The rule is adds S.
Mm-hmm.
So the minimalist view is that the lexicon stores the root book. When you move it to the numeration to your shopping basket, that's when you add an optional feature, like plural.
That actually blows my mind a little bit. I always pictured my brain having this massive scroll with every version of every word, but you're saying I just have the roots.
You have the roots and the rules to modify them. It's about optimal coding. The text says, only store the exception. Build the rest. Case is the same. The words he and him probably come from the same root, and you just add a case feature subject versus object when you pull it out for a sentence.
So I go to the store, I pick up the generic concept of book, and as I'm putting it in my basket, I slap a little sticker on it that says plural.
That's a great way to think about it. And that sticker is the feature that the machine is going to process later on.
It all connects back to that perfect language idea, doesn't it? The system is designed to be as lean as possible.
Lean, efficient, and, as the text concludes, potentially therapeutic.
That was a funny word to find in a linguistics paper. Therapeutic. What on earth did they mean by that? Are linguists in need of therapy?
Well, arguably, yes. But here it refers to a kind of scientific honesty. The minimalist program forces linguists to stop inventing complex rules just to describe phenomena. It forces you to ask, is this rule I'm proposing actually necessary? Or am I just restating the problem with a new name?
It's a razor. Occam's razor.
It is. By stripping the engine down to just select, merge, and feature checking, you get to see what's really there. You stop adding extra complexity where it doesn't belong.
It clears the fog.
It does. And it leads to that final, really kind of mind-bending thought that the text leaves us with. We see all this complexity spell out, movement, checking strong features, all these crash scenarios. It looks messy. We just spent 20 minutes talking about how expensive and complicated movement is.
Right. It feels like a workaround, like there's duct tape on the engine.
Exactly. But the text suggests that
Yeah.
maybe the core language system itself is actually perfect.
But we just said it was messy. We have to move words around because of strong features and spell out.
We said the implementation was messy. The text speculates that these so-called imperfections, like having to move words around, might just be extraneous requirements imposed by the fact that we have, well, bodies.
Because we have to use sound.
Because we have a sensoromotor system. We have mouths that can only make one sound at a time. We have ears that process sound in a linear sequence. What if we didn't have bodies?
If we were just floating minds.
If we were disembodied minds communicating via pure telepathy, we wouldn't need sound. And if you don't need sound, you don't need spell out. If you don't need spell out, you don't need to strip away features. And if you don't need to strip away features, you probably don't need to move words around to check them before the stripping happens.
So the mess isn't the software, the mess is the hardware driver.
That's the hypothesis. The core language faculty might be this perfect crystal of logic that is unfortunately trapped inside a noisy biological primate body. We have to engage in all this messy movement and spell out stuff just to get the data out through our mouths and into someone else's ears.
That is a wild thought to end on. We're running perfect software on glitchy hardware.
And we're doing the best we can with it.
Well, I'm definitely going to be thinking about that hot potato every time I ask a question today. And I'll try to appreciate the efficiency of my mental dictionary, even if it doesn't actually have the word books in it. Thanks for guiding us through the machine.
It was a pleasure.
And thank you for listening to The Deep Dive. We'll catch you on the next one.